the intersection of the convex hull with the circle will be exactly this subset. So really it is shattered. So the VC dimension of this is big. And we said that if the VC dimension is big, there is no hope for small, strong epsilon nets. In fact, we would need to take almost all points for strong epsilon nets. But actually, weak, we could do it. And here is a definition. So what is weak epsilon nets for convex sets? So we said what is a general definition, but let's say it in this example. So we have n points in the d-dimensional space. Here you have maybe 10 points in the 2-dimensional space, and we have some epsilon, and maybe in this example, epsilon will be 0.4. Okay, so epsilon n is 4 points. And our objective is to construct a point set Y that stabs all the convex hulls of at least epsilon n points of A. So whenever I take a convex set that contains at least 4 points of A, namely whenever I take the convex hull of at least 4 points, or exactly 4 points, it should contain one of these blue points that you see here. So I picked here some points, some blue points, maybe 6 blue points that you see, and this is Y, and you see that Y is not a subset of the set denoted here by, I don't know, A, right? So it's not a subset, but still it is the case that whenever you take, there are a few examples here, here is some convex hull of 4 points, and you see that it contains one of the blue points. Here is another one, convex hull of 4 points, and here is another one, here is another one. All of them contain some blue point. So this is indeed a weak epsilon A. Okay. And indeed the statement is, so again it's stressed here that the points of Y do not have to come from A. That's why this net is called weak. Okay. And it turns out that one can show that, this is an odd result, that for any finite set of points in the plane, there is always a weak epsilon net of size maybe 7 over epsilon squared for the family of all convex sets in the plane. And something similar holds for higher dimension as well, but not state it precisely. And this is useful, so again, I want to, so there is this pressure of say 48 minutes, so let me just say something very quickly. So one motivation for weak epsilon nets was a question of Hadwiger and de Brunner, so that was called the PQ problem. It was raised in the 50s, and this is something that we proved with Lenny Kleitman. So the question was the following. It's an extension of Haley's theorem. Suppose that we have compact convex sets in the plane, and whenever we take P of them, then some Q among these P contain a common point. There is a one point that pierces all of them. Then the conjecture said that we can intersect all points by all convex sets by some finitely many points, some function of this P, Q, and 2, and not the size of the family. Okay. And again, there is a higher dimensional extension, and this turns out to be true. And somehow the notion of weak epsilon net is crucial here. And let me just maybe, so here I'll explain why this is an extension of Haley's theorem, but let's ignore it for now. So you see the connection comes from the fact that here is what would be a good example with PQ property. So one example that you can take some family of n points in the plane, and now take all convex sets that contain at least a fraction or more than a fraction q minus 1 n over p of them. So then whenever you take p sets, then the sum of their sizes in terms of the number of points they contain is more than q minus 1 times n. So by pigeonhole, some point will have to belong to at least Q of the sets. Right? And here you see that exactly if we take Q minus 1 over P net for convex sets, for these sets, we will indeed intersect all convex sets that contain at least z fraction of the number of points, because z was the definition. So this shows that at least it is relevant for the Hadwiger-de Brunner problem, and it turns out that one can combine it with something called fractional Helly's theorem, and with something else that some duality, basically the minimax theorem, and get a proof of this result. So let me skip a little bit. Well, you could look at the picture, and let me skip this and tell you something about it. But I want to show you one proof. There is a very simple proof here, and he's going to say that every talk should contain one proof and one joke, and they better not be the same. So let's try to show you one proof. There is really so there is some proof here that is very simple, and I can almost describe it. And the only thing about it, so it's very simple, but it applies something deep, and the something deep that it applies is what's called the density Hayes-Jewett theorem. Now, when these days you prepare PowerPoint presentations, you want a picture. So how do you get it? You go to Google Images, you write, in this case, Hayes-Jewett or density Hayes-Jewett theorem. This is what you get. You don't know what is the connection. Actually, in this particular case, I really looked, and the picture appeared in a blog by someone, I forget who, and he has this picture, and then he writes below it that this picture has no connection whatsoever to the Hayes-Jewett theorem, but the trouble is that there are no good pictures, and I wanted to put something, so this is what I chose. Okay, so I copied it. But, all right, so let me tell you what is this density Hayes-Jewett theorem. So for that, we have to define a combinatorial line. So we look at the set of all vectors of length d, dimension d, with alphabet 1 up to k. So I denote it here by this k to the d. All right. It's better to look at the example, but let me still read what is written here. So I want to define a combinatorial line. So what is a combinatorial line? It's what you see in the example here. So it's a set of k points, in this case k is 3, k vectors of length d. And then there are some indices, and you see it here, here in this example, these are the second index and the fourth index, which are constant in all the points. And the other indices, in the first point, all of them are 1, in the second point, all of them are 2, in the third, all of them are 3, and so on. So this is called the combinatorial line. So again, it's a set of k vectors. They are fixed in some coordinate. In all the other coordinates, in the first point, they are all 1, in the second, they are all 2, in the third, they are all 3, and so on. You see, this is also, if you think about these points really as points in the d-dimensional Euclidean space, this is also a line. All these points lie on a line in the d-dimensional space, right? But we call it the combinatorial line. Okay, so there is this result, it's called the density Hayes-Jewett theorem. It's an extension of Semrely's theorem. It gives it a special case. That was proved by Fierson and Katzenelson, first for k equals 3, which is a bit easier than the general case, and then for the general case. And what that basically says, say that for every k, if the dimension d, and for every delta, if the dimension d is big enough, then even if we take just a very small fraction, delta fraction of the total number of points, then this contains a combinatorial line. You see, there are so many combinatorial lines because we're being very high dimension that even if we take just 1% of the points, then always there will be a combinatorial line if the dimension is big enough. And you see, this is very good for us because it says something very close to the thing I want for my construction.
Is it an elementary proof by now, or is only proof is algorithmic?
No, so I'll come to that. That's supposed to be the experimental, semi-experimental part. So there is a more effective part. But these proofs are ergodic theory. Let me come back to that maybe in the next slide, or maybe 2 more slides. So look at the range space whose points are all these vectors in k to the d. right? So these are the points. It lies in d-dimensional space. Now d is huge. So it's not, we want something in low dimension, but still, d is huge. And the ranges are lines, combinatorial lines, but these combinatorial lines are also lines. So these are the ranges. Now, just because of this, you plug in it. If you define epsilon to be k over k to the d, so very small, it means that you have to capture every line, every combinatorial line, because every combinatorial line contains exactly k points. And what this tells you is that you have to pick almost all the points for that. Really, 1 minus delta fraction of the point, let's say at least half of the points. So this is much more than 1 over epsilon, because 1 over epsilon, it exceeds it by a factor of k. Okay, so this will be by more than a constant factor. And the only trouble is that the dimension here is very big, but in fact this is not a real trouble, because what you can do is just take all this configuration and project it randomly into the plane. And if you do it a generic projection, then there will be no coincidences. And the only way to capture a combinatorial line, the projection of a combinatorial line, would be by picking one of the points of this line. No point of some other line will fall on the same geometric line. So this is just by the property of the probabilistic thing. And this basically gives it, if we go back to what estimate does this give, so the proof of Katzanelson uses indeed tools from chromatic theory, and it's non-effective. So it just will tell us that the thing is nonlinear, but it will not tell us any function, any explicit specific function. But actually, there is a more recent proof, and that's a proof obtained by the very first Polymath project. So this is kind of an experimental thing, maybe not in the sense meant by the title of the seminar, but let me tell you about this anyway, if you haven't heard about this before. So this was an attempt initiated by Tim Gowers to see if people can work on a problem, on a mathematical problem, without ever meeting and without ever hearing about each other before. So the idea is that you take a problem, you post it on the web, and you have some convenient interface, and anybody can post comments. So anybody that in the world that has access to the internet can look at this problem and can write what he thinks. I mean, you'd think that this would be a total chaos, and it will be completely impossible to follow, and mostly everything will be nonsense. But some of the hope was that this would work, and there were some precise rules of how exactly to do this. And the very first example that they tried was to find a combinatorial, more elementary proof of this density L-Jewett theorem. And in fact, for k equals 3. And this started in January 2009. And actually, after 37, so this was extremely successful. So after 37 days, they had a proof, not only for k, but for the general case. And it's combinatorial, and because of this it's effective. It gives some estimates. This estimate is bad, so it's inverse Ackermann, but still some specific estimate. I should say that it's not clear how successful it was in terms of Polymath, because the number, so many people posted comments, but indeed most of them had kind of nothing, a comment, I don't understand what is a line, can you explain something like this? But in the final proof, maybe only 6 or 7 people took really part, so it's not more maybe than a usual paper with many co-authors. And maybe another discouraging fact is that since then, they tried at least 10 more problems, and there was no essential progress on any of them. So maybe the first one was just lucky, but still this as a notion is interesting. I mean, is it possible? So this was kind of an experiment of something new, and it's interesting to see how this will develop in time. Because definitely the internet enables us to do things that we couldn't do before. So this is But still, so this gives us some specific estimate, and I just want to mention that what I kind of sketched is the proof for the strong nets, which indeed is more or less immediate from the first Katzanelson. Once you decide to use this density Hess-Jewett. But if you want to do it for weak nets, then you have to work a bit more, right? Because for weak nets, the points that you choose are not necessarily from the lines themselves. So you still have to worry that maybe you will choose some points that will capture many lines, although they are not projections of the points of these lines. But this can be done as well. And let me just finish with two philosophical comments and one problem. There are several open problems, but maybe I just mention one of them. I think I still have 2 minutes according to my watch. So the two kind of semi-philosophical, well, not very deep philosophy.
Yes.
So the first one, and it happens several times, so I think it's good to remember it. I told you that there was this conjecture, and it was proved in many special cases, and each of them seemed to require some new ideas. And it seems that when there is a conjecture and the proofs in special cases begin to be more and more complicated as the cases become more complicated, so one should consider also the possibility that the general case is false. It's not always happens, but definitely it happens several times. And maybe another thing that, of course, we all know, but let me state it anyway, is that deep results like this density Hess-Jewett theorem, this is almost a definition of deep results, they often lead to interesting consequences. So you just, often you just have to use them, and then they lead to something interesting. And let me just mention one problem. So I'm pretty sure there are more problems, but I think this one is nice. So I'm pretty sure that the minimum size of epsilon nets for some finite point sets in the plane with respect to lines, so really the range space that we considered in the example before, so we know that the size has to be at least 1 over epsilon times some inverse Ackermann, but I think that there are examples for which it should be 1 over epsilon log of 1 over epsilon, and I even can tell you which example I believe, so I don't know to prove it, but I think that the following holds. So we'll just take a grid of, I don't know, a k by k cube points, usual grid. So this has all kinds of lines that contain k points, right? The horizontal lines, the lines like this, all the lines that contain exactly 1 point from each column. We have these k columns, and we have okay. So now just take a random subset of this. Each point, choose it with probability half. So you'll have about half of these points. And most of these lines that before contained k points, now they will contain about k over 2 points. So let's say that we want to capture all lines that contain k over 3 points of what's left. So the configuration of points is just a random subset of the grid points. The lines are lines, and the epsilon is such that I want to catch all the lines that still contain at least k over 3 points. Then I think the best that we can do is to take about log k columns, right? So this will, with high probability, capture everything. And I don't think that there is a better way, but I don't know to prove it. So, so this is a conjecture. And with this, let me finish, and thank you for your attention.
Noga, we get to answer questions in private. Thank you. Also, if you'd like to join us for dinner at 6:45, let me know right now. Thank you.